Okay, so far, all of our applications of our brand new third hand rule have involved a moving charge that is confined to a conductor, right? Confined to a wire, so that when the magnetic force pops up, right, it moves the conductor itself. It's not just moving a single charge. It's not just acting on a free charge that is not kind of confined to a wire. Um, so the third hand rule, it actually applies completely the same way to free charges, ones that are not confined to a wire. Okay, so just to show you what that might look like, I'm going to show you a quick demonstration. Okay, but then we'll come back and look at some of the more math-based analysis of this. Okay, so before I go ahead and do this from above, because that's kind of where we need to be to really look at it, I'm just going to show you the setup so you can kind of see what I'm talking about. It won't be as clear from above. So all I have here are two two rulers wrapped in tinfoil, right? Tinfoil so that it is covered in metal and it conducts. So essentially what I'm going to have are two parallel plates, two conducting parallel plates. So um, if I hook those up to a battery, right, if I connect each parallel plate to a battery, you'll see when I hook it up what it'll look like, but I'm just going to hook each to a terminal of the battery, and that will negatively charge one plate and positively charge the other plate. So there will be an electric field between the two plates. Okay. The other thing I'm going to do, I'm going to add some salt. This is leftover salt water that you can see has evaporated and crystallized a bit. So this is all just table salt, sodium chloride. Okay. I've actually already added some in there, but just so you can watch me do it, I'm just sprinkling table salt in there, okay? And we'll see why when I go to it. I just wanted to show you the setup from another angle before I actually do the demo. Okay, so here's what the setup's gonna look like. I'm gonna unhook it. First, we're gonna kind of analyze the situation with our hand rules and stuff first and kind of make some predictions, but you can just kind of see here how it's going to look once I hook it up, right? So I have the positive plate here connected to the positive terminal. Electrons are flowing from here and building up on this plate. You can actually see that bubbling. That is some that is a clear sign that electricity is being produced. So the bubbles there forming were actually hydrogen and oxygen. We were doing, it's called electrolysis of water, splitting H2O into, well, H2 and O2. But that's not actually, it's not the purpose of this, okay? So I just wanted to show you the setup there. We have an electric field across. Now let's think about what's happening for each charge. So I'm just gonna move this for a sec, okay? Remember how I had it hooked up? Okay, so I had my cable that goes to my negative terminal, the black one, right? I had that hooked up to, okay, so that would be my negatively charged plate. And then I had this one hooked up, so I have my positively charged plate. So here I should have used red and black for color coding, but I've kind of been using blue for positive and red for negative, so I'll stick with that. Okay, now what did I put in the solution again? I put into there sodium chloride, right? Table salt. If you've taken chemistry at all, right, you know that sodium chloride is very soluble, and when you put it in, it will dissociate into its ions, right? Ionic compound. You all know that word from Science 10. Ionic compound meaning made up of ions, which are just charged particles. What makes up sodium chloride? Well, there's positive sodium, right? Positive sodium, and there's the negative chloride, okay? And so there are tons of those floating around in here, right? Literally billions and billions of them floating around in there. Tons of those little ions, those charged particles. Okay, so if they're charged, what are they going to want to do? Well, they're going to want to do two different things. Chapter 11, right? The chloride is going to want to go towards the positively charged plate. The sodium is going to want to go towards the negative charged plate. So what is that going to do? It's going to make them move. They're going to have some speed, right? So that will be how sodium will want to move. That will be how chloride will want to move. Okay, so that was happening when I hooked up the current. The thing is, it wasn't that interesting yet because, well, they would just kind of do that. We also can't see them. Ions in solution, right? A true solution, you can't see anything in there. It's a uniform mixture. But how could we make this a little more interesting? Well, what if I were to bring a magnetic field into the mixture? Okay, so these free charges that are floating around in solution, they're not in a conductor. I'm going to bring a magnetic field into the equation here. So I have here a fairly powerful neodymium magnet. Okay, let's take a look. Let's figure out what its north pole is and what its south pole is. Okay, so there the field is pointed towards the magnet, right? And there it's pointed away. So field lines should enter south. So that must be south and leave north. Okay, so that's north. So I'm going to put it north side up. So what do the field lines look like? Well, if we use our compass to check, right? They are coming at us. So if I put this, I'm going to put this underneath my whole setup so that, right, I'm going to sit this on top of the magnet so that then what do the field lines look like? The magnetic field lines. Well, they are like all other magnetic field lines. They're leaving the North Pole, right? Yes, they're going to loop around back to the South Pole, but where they're strongest, they're going to be leaving the North Pole, where they're the strongest for our apparatus, right? They're very strongly leaving out. Right here, quite strong, okay? They are coming up out of the plane. They're coming out of the plane of the board right at us where I'm going to actually look, okay? So I'm going to do a test to see what's happening at this point. I'm just drawing these over here to give myself some room to draw everything. Okay, now ask yourself, if you're a positive ion, if you're a positive charge, you've been given a speed because of the electric field, right? You have motion because of the electric field. If there's a magnetic field there as well, will you feel a force? So are you perpendicular to this magnetic field? While the magnetic field is out of the plane, right, of the page, your velocity looks like this. So yeah, it is perpendicular, right? 90 degrees. As we know, if there's an external magnetic field and a moving charge with a perpendicular component to that magnetic field, then it will experience a magnetic force. Now, positive charge, which hand rule? Use your right hand rule for a positive charge. Okay, the magnetic field is coming out of the plane of the page at you, and the charges should be moving this way. Okay, I have to bend my thumb a bit. So which way should it feel a force? Its magnetic force should feel a magnetic force this way, right? So the initial first kind of push that it feels from this motion should be that way, right? That should be kind of the first thing it feels. Okay, and we'll get to what it keeps doing after that, but just right off the bat, initially it's going to feel a deflective force that way, right? What about the chloride ion? Well, left-hand rule, and it's also moving the other way, but the magnetic field hasn't changed, so what does it feel? Aha, it actually feels the same thing, right? It actually feels a force in the same direction towards the left side of the board here. So same thing goes for chloride. Okay, so what that means then is that we have all of these ions, whether they're positive or negative, that are floating around in here, right? All of them are feeling that magnetic deflective force to the left. Now, well, if I hook it up, they will be, okay? Or they should be according to our hand rule. Now, how can we see that? Well, we kind of can't, right? We can't see the ions moving. However, if all of those ions are moving, they are kind of going to be creating a bit of a current, a bit of a pull. That's actually how a lot of currents in the ocean come from. They come from salt ions moving from places of high concentration to places of low concentration. So we should get a bit of a current at that point. So if I were to sort of color the water there, we might be able to analyze how the ions are moving within the solution because of that magnetic force. Okay, so there we go, two parallel oppositely charged plates with a magnetic field coming out of the plane of the page and a bunch of ions to move around. I'm going to drop in a little bit of food coloring and we'll see what happens. Notice which way it's all kind of going. There's a little bit of a current going on here. And normally when you drop food coloring into water, it spreads out pretty quick, right? It diffuses around. Notice it's all kind of sticking over there to the left. You can see that. Oh, wow. Do you see that? Look at that current down there as it goes. There's an immediate kind of whoosh pull. So the ions, as we saw with our hand rule, are all being pushed that way. And as those ions flow through the water that way, they kind of create a current that way. Why are they all flowing that way? Well, just a magnetic force. That is so cool. Okay, so when a free moving charge enters a magnetic field perpendicular to the field, okay, so when a free moving charge enters a magnetic field, it is not going to stay within that wire. If it's not in a wire, if it's just a free, for example, an electron flying through, or a proton flying through, or an oxygen ion, or whatever flying through, it can be, there's not a wire that it's stuck in. So it's able to move. Its trajectory can be changed, right? And it says the force there. What kind of force? What are we talking about? We're talking about Fm, right? The magnetic force, okay? It can change its trajectory. Will it? It will. as long as if, as long as V has a perpendicular component to B, the magnetic field, right? Okay, so the example one there asks us, kind of using the ones below, what type of motion are we looking at? Okay, so to figure that out, let's use our hand rules and think about what's going on here. So in the first one on the left-hand side there, we have a positive charge, okay? A positive charge entering a magnetic field that it is indeed perpendicular to. Okay, so there's our perpendicular magnetic field. And they've drawn the force in for us, but let's see how they got that. So they had a positive charge, okay, right hand rule, entering a magnetic field that leaves north, enters south, so that goes like that. And notice, okay, at first, what kind of force is it going to feel? First, it's going to feel a force up. Okay, great. But then it's going to accelerate up, right? As you push it up, it's going to change its motion up. Okay, great. Now its velocity, right? Now its velocity is still perpendicular to the field, right? And so, but the magnetic field hasn't changed. So you're going to feel a force kind of this way now, right? Now that its velocity has a bit of an upward component, magnetic field hasn't changed. Notice how the force is kind of curving, right? So the force is now inward a little bit more, right? Now it's that way. If you're saying to yourself right now, but hang on, it's not perpendicular to the field if it's moving up. Be careful, right? Well, let's think about this carefully, okay? So let's just say, obviously kind of not really from this perspective, but let's say our velocity goes like that, okay? And our force goes up, and let's say our magnetic field kind of goes away from us like that. Okay with that? Okay, so our magnetic field kind of goes like that. All right, so we're saying that this force is going to cause the velocity to change upward. It's going to make it accelerate, right? A force can cause an acceleration. What's an acceleration? It's just the rate of change of the velocity. So if there's an upward force, there'll be an upward acceleration, which means the velocity is going to gain more and more kind of upward components. Now notice, as I make this go more and more and more and more up, or even all the way up, does that ever change the perpendicularity, okay, of the velocity to the magnetic field that it's traveling through? No, right? I can go all the way around, and at no point is the angle here no longer 90 degrees. The velocity can go all the way around, and at no point does it end up not being at 90 degrees to that magnetic field. So the force, that magnetic force, doesn't disappear because, yes, it's changing its motion, but it's changing its motion in this plane, which is that plane, its entire plane of motion here. Do you see they've even kind of highlighted it? It looks like a frame of glass. That entire plane is perpendicular to the magnetic field. Okay, let's look at the next one. On this one, we have, what kind of charge is this? Is it positive or negative? They actually don't tell us. Let's figure it out. So we have magnetic field lines leaving north, going to south. Okay, I'm going to use this point here just to think about. If this is a negative charge, let's try that. So if it's negative, either way, the magnetic field is down that way. My hand would be going that way, which would say the force should be out towards the page. Nope, that doesn't make sense because how could this thing be pushed? How could this thing's velocity be kind of changed inward if the force was outward like that? So that can't be right. This must be a positive charge. So whatever this thing is, it is a positive charge, okay, positive charge. Now notice, take your right hand, go all the way around. Notice, since the force is in, its velocity is constantly going to be kind of changing in a bit, right? So the velocity is kind of changing in, and the force is always going to be changing with that velocity. So since there's an inward force, as soon as that velocity changes, so too does the force, kind of by our right hand rule, right? So you're kind of scooping it around like that. If we were to view it from above, what would we see? We would see it go like that. The force kind of always keeping it in. This force, notice it's always kind of center seeking. It's always causing this thing to accelerate in towards the center. Hey, does this sound familiar from Physics 20? What kind of motion is this? This is circular motion, right? This is uniform circular motion. There is a centripetal force. In this case, it is the magnetic force. It's a center-seeking force. It's constantly radially inward by our right hand or left hand rule, right? As the velocity changes, so too does the force, and vice versa. The force is causing the velocity to change in the first place. Notice the perpendicularity thing is not broken here. At every point, the velocity is still perpendicular to the magnetic field, and it's perpendicular to the force, and same goes for the force. The force is perpendicular to the magnetic field and perpendicular to the velocity, right? Because this entire plane here, this entire plane that this circle exists in, is perpendicular to that magnetic field, right? That whole plane there, that whole flat circular area is perpendicular there. So everywhere in there, the velocity is still perpendicular as it's changing. Okay, so what type of motion is this? As we saw there, right, with our hand rule, this is going to cause circular motion. So circular. Okay, so this is a physics principle. Uniform circular motion is a physics principle. If you flip over the back of your data sheet to get the number, it's one you haven't really used since physics 20 until today. That is physics principle 2. Okay, so remember when we were doing electric fields? Let's just, again, remind ourselves. Remember when we were doing electric fields and we had a positive plate and we had a negative plate and a charged particle entered? What did we say the path would look like? We said it would be parabolic, right? Or parabola shaped, because at no point along there is there any x direction force, right? It's going to get pulled towards the negative plate. There's only ever a y force, right? There's nothing in the x-axis to actually make it change its motion in the x-axis. Now we are in a perpendicular magnetic field. So that is actually no longer the case, right? If I take some particle and I send it in there, okay? If I take some particle and I send it in there, at that point, let's just say this thing is negative, for example, an electron. Well, now this thing does have, at that point, it feels, sure, initially it only feels a y force. The Fm at that point, if you use your hand rule, would be down, right? But again, now there is an x component because all that has to do, all that Fm is perpendicular to the velocity. So as the force causes a change in the velocity, it's kind of also causing a change in itself because it's perpendicular to the v, right? It's kind of a self-feeding cycle here. F changes v, which changes F, which changes v, which changes F, so that eternally they're kind of, so that they're going like that, right? F is always radially inward. Okay, just like when you had a ball on a string and you were whipping it around in physics 20, right? If you were twirling this around, the tension in radially inward was called a centripetal force, right? A center-seeking force, which was causing the velocity to change. It was always tangential, right? Same thing here. The velocity is always tangential, but it is constantly changing, right? It's always, the velocity is tangential, but it's constantly being accelerated inward by this center-seeking force. You might remember in gravity, same thing went for gravity, right? Why do the astronauts on the space station float? Not because there's no gravity out there. If you do Fg equals gmm squared where the space station is at, you're going to get pretty close to 9.81. Okay, it's not that different. Okay, the reason is that they are constantly kind of going sideways. They're just going side, and they're constantly kind of falling. Gravity is constantly accelerating them towards Earth. They just have enough sideways motion to always miss the Earth as they're falling. Okay, so just a bit of a quick crash course reminder on circular motion. The force is causing the velocity to curve inward, which causes the force to curve inward, which causes the velocity to curve inward, so that we get this centripetal force. Okay, so it asks us to derive the equation to determine the magnitude of the magnetic field if we have some information here. So, well, we know that the magnetic force now, okay, is equal to something we haven't seen in a little bit, but it is now a centripetal force. The magnetic force is a centripetal force when we have this kind of motion. Okay, we have a couple equations. MFM. Well, this is a free charge, so it's going to make the most sense for us to use Q V perpendicular. The charge's perpendicular component of its velocity to the magnetic field, and then that magnetic field. Okay, QVB is equal to FC. Remember what FC is? Well, every F is an MA, right? Every F is an MA. So centripetal forces is just mass times the centripetal acceleration. Now, this equation isn't actually on your formula sheet. However, this one is. This one is. Okay? The centripetal acceleration is equal to the velocity, the tangential velocity squared over r. The tangential velocity, since at all points on this circle is perpendicular, right? Then v here is actually the same thing as v here. Okay, so let's just rewrite this then. So qv perpendicular times the magnetic field is equal to m. Now AC is going to be mv squared over r. Remember this? Fc equals mv squared over r. You're getting flashbacks to physics 20. Okay, there we go. So now, what did it ask me to do? It asked me to derive an equation to determine the magnitude of the magnetic field. So let's just divide both sides by qv perpendicular, okay? And so we're given that the magnitude of the magnetic field is equal to, okay, mv squared over rq v perpendicular. And again, v and v perpendicular are the same thing here, right? V is always perpendicular, okay? At least the ones we're going to analyze. It's possible for it not to be, but we won't have to analyze those. You can read your textbook if you'd like to see what they look like. For now, in the interest of time, we're not going to worry about it. But v squared over v, that's the same thing. So squared and v are gone. And so the magnetic field strength, the magnitude of it is equal to mv over qr. So the mass of the particle entering, the velocity at which it entered, the charge of the particle, and the radius. Hey, look, we can actually, if we know our magnetic field strength, we know the velocity it entered at, by just measuring something's radius of curvature, we can actually figure out what kind of particle it is, right? This is actually something that is often used to determine particles that are flying through space. For example, I know at the University of Alberta, they have a big and it's not even like a big piece of research equipment. It's just kind of something cool you can stop in and look at in their physics building, right? It's called a bubble chamber. So it's essentially what it is you look at it and you constantly just kind of see these little spirals that come in, right? And by looking at the radius of the curvature that it follows, okay, looking at knowing the magnetic field strength, because you kind of set that, well, then you can figure out the mass to charge ratio, charge to mass ratio, and actually then figure out what particle it is. Pretty cool. Okay, so we have a magnetic field is directed into the page. So why am I drawing X's? Well, those are the tail feathers of the magnetic field as it goes into the page. Okay, so there's a magnetic field. Now, particles fly in from the left. Describe the motion if the particle is an A electron. So let's do A. If I have an electron and it flies in from the left, let's assume they all fly in at about the same speed, okay? If it flies in from the left, so that's its kind of V to start with. What is its path going to look like? Well, it's negative, so we'll use our left-hand rule, okay? Thumb is the direction of motion of the particle. So thumb is the motion of the speed of the particle. Fingers are the magnetic field. Where's the magnetic field? Well, it's into the page. So what kind of force is it going to feel? It's going to feel a downward force at first, right? At first it feels that downward force. But then its V changes a bit like this. So now the force is a little bit like that. Then the V changes again. It's a little bit like that. The V gets changed a little bit more. It's like that. The V actually gets changed so much that eventually it's up, the opposite of where it started, right? And then it kind of keeps changing and it's in, it's in, it's in. And what do we have now? We have circular motion, right? This is no different than a ball on a string, right? If I swing a ball on a string, the tension in the string constantly pulls it back in, constantly causes the V to change so that the force is always inward and the ball is always technically accelerating inward, right? Or a planet orbiting something else where the force of gravity is the centripetal force. Now the magnetic force is the centripetal force. Okay, so what will this thing do? It will come in, it will, right, constantly feel a force in like this, right? Initially, that will be FM, and then that will be FM, and then that will be FM, always perpendicular to both the magnetic field and the V, right? And eventually, this thing will enter circular motion, the path looking something like that, okay? Now we're going to have to, now that the first one, okay, sure, we can draw it kind of however we want as long as we curl it right. We're going to have to think about how the next ones are going to compare. So what about a proton? So be a proton. Okay, so a proton is going to enter this magnetic field. And what's it going to do? Well, which hand rule? Right for the positive charge. Okay, great. So it's going to come in. Now, it is going to feel a force upward instead of, or towards the top of the board instead of towards the bottom of the board, unlike the electron, right? Now let's think about what does the path of the thing, of the charge depend on, or the particle depend on while it's in the field. So I'm just going to remind ourselves, Fm equals Q V, and we assume they all are going to have about the same V, times the strength of magnetic field. Well, they're all going through the same magnetic field. Okay, so between an electron and a proton, are they going to feel any different kind of magnetic force? No, right? They should feel the same magnetic force. Okay, great. But will that force affect them both the same? So remember, Fm, right? The centripetal force is going to equal the magnetic force. And what is a centripetal force? Well, it's the mass times the centripetal acceleration, right? Which is, well, it's mv squared over r, right? So mv squared over r equals qvb. So when we're drawing the path, what are we really needing to think about? We're really needing to think about r, right? When I go to make proton, the p, I know it's going to go up, but is it going to go up faster? Is it going to go up slower? Well, let's just kind of see the dependency. Let's just see what r really depends on, okay? So if I, just because that's really what we're interested in here, right? R, if I bring it up here and then divide both sides by QVB, and then I have V squared over V. Okay, so R depends on the mass, the speed at which it enters, which you said is going to be constant, the charge, and the magnetic field, which is also going to be constant. Okay, so between an electron and a proton, the charge does not change, right? However, the mass changes a lot, right? The mass changes a lot. You can even think, yes, this is nice to have now, but think about F equals ma, right? Is this proton's acceleration going to be the same? Of course not, right? Its mass is, a proton is about 1,800 times more heavy than an electron, or more massive, I should say, than an electron, right? So its path is definitely going to be, well, let's see. If I make the mass bigger, right? If I make this number bigger, what happens to the radius of curvature? Well, if I make m bigger, so r gets a lot bigger too, right? Well, that makes sense. If it's way heavier, the same force isn't going to affect its motion as much. So it's going to, this is not to scale, by the way, but it'll do something like that. The circle will be a lot bigger if this magnetic field is even big enough to, right, for it to not escape and end up doing its own thing. See, an alpha particle. What is an alpha particle? Again, and it's just a helium nucleus, right? So essentially, take a helium atom, kick off the electrons. You got two protons, two neutrons. However, that does not weigh the same as two protons and two neutrons. We'll get to that in our last unit, okay? But for now, C, alpha particle is on the mass of an alpha particle is on the back of your periodic table. It is 6.65 times 10 to the negative 27 kilograms. All we super need to know right now, because we're just kind of getting a feel for these concepts, is that compared to the proton, its mass is bigger, right? Its mass is bigger. That's alpha for alpha particle. Okay, its mass is bigger, about six. Its mass is bigger than a proton, about 4 times bigger mass. Don't forget though, right? The charge of an alpha particle is plus 2e because there's two protons in there. So the charge, and again, that's on the back of your periodic table. So it's plus 2 times the charge of a proton. So so yes, the radius of curvature will be bigger, but it's not going to be 4 times bigger. It'll be 4 over 2 or twice as big, right? So let's draw it bigger, the radius bigger, but not 4 times bigger. So roughly, maybe something like that. Okay, but I forgot to use my hand rule there. That was the whole point. Y still up, it's a positive charge, so right hand, okay, it's moving that way. Magnetic field is still into the plane, so just ever so slightly getting. The force is actually bigger here, right? It's double the force, however, it's 4 times the mass, so it works out to half the acceleration and therefore half the radius, okay? But just getting pushed there. Okay, let's look at D, a neutron. D, a neutron. Okay, so yes, according to this equation, what's the charge of a neutron? 0. So R goes to infinity, right? Do you know what a circle with a radius of curvature of infinity looks like? It's kind of a silly question at first, right? But it actually kind of does exist. A circle with a radius of curvature of infinity actually is a straight line. We'll get there without having to think of it that way, though, right? Remember, don't get lost in this equation. This is helpful when we're looking at stuff that is going to curve, but how do you get a magnetic force? Fm equals QVB. Hey, if Q is 0, what's F? 0, right? Okay, so as this particle, first of all, which hand rule do you use? You kind of can't use either one. There's a clue too, right? It's not negative, it's not positive. So if there's no hand rule to be used, there's a good clue, okay? Now, a neutron will not experience any force. So will it deflect up? Will it deflect down? Nope. What will the path of a neutron look like? And that goes for any neutral particle, right? You must have a charge to feel a magnetic force in a perpendicular field. Okay, sorry, you are going to see a few things. You are going to see all the math here kind of worked out while I'm still talking about setting up the scenario. And then you are going to see once I'm later, when I'm working out the math, you're going to see a different picture up here. That's because I did not read very carefully and I did the whole problem at first as if it was an electron. And at the end, when I was about to put in my numbers, I realized it was never an electron. It was supposed to be an alpha particle. So I had to go back, fix my picture. And then, so that's why you'll kind of see it change. That's just why you're seeing stuff out of order, sort of. Okay, so let's actually try to do some calculations with this now, some hard calculation. Well, okay, so let's actually try to do some calculations with this now. So example 3, an alpha particle is accelerating to 0.85 c. Remember c, the speed of light on the back of your periodic or your data sheet. Taught too much chemistry recently. To the right, when it enters a perpendicular magnetic field, a perpendicular magnetic field of 1.2 Tesla into the plane of the page. What will be the direction and radius of curvature of the path? I'm just going to take out that word direction, because what's the direction of a radius? There are times in your physics and in your math, you will think of radius as having a direction, but realistically for us, the radius is exactly what it sounds like. It's half of the circular path that it's going to take. If you wanted to give it a direction, you could say it's radially inward. I'm not really going to do that here though. So let's just find how big the radius of curvature will be. What we will do is conceptualize the direction that it will move, right? Will it move counterclockwise or clockwise? That's what. First, let's draw it so we can figure that out. So it's accelerating to the right when it enters a perpendicular magnetic. So there's our magnetic field into the page. I'm going to draw our alpha particle over here. Okay, and our alpha particle is moving to the right with some v, okay, with some v, which we know is 85% the speed of light by the time it gets there, okay? First things first, which way is the initial force that it's going to feel, the initial magnetic force once it enters this field? So left-hand rule or right-hand rule? Well, an alpha particle, remember, an alpha particle has a charge of plus 2e. Okay, that's on the back of your formula sheet, which makes sense. It's just a helium nucleus. So it has the same charge as 2 protons, right? The 2 protons in a helium nucleus. So it has a positive charge. So this is going to be our right-hand rule, the third hand rule, right-hand version, right? Because it's entering a perpendicular magnetic field and we're trying to figure out the force that it will feel. So as it enters, okay, if you take your right hand, I want you to try this, follow along, take your right thumb, and that will be the direction of particle motion. Then take your fingers, point those in the direction of the magnetic field. So right now your finger should be pointing into the screen and your right thumb should be pointing to the right of the screen. And what does that mean your hand is doing? Well, it's pointing up towards the top of the screen, right? So you kind of would be holding out your hand like you're asking for money or something, okay? So the magnetic force at that point would be what your palm is trying to push it, right? So up, that would be Fm. Now initially it would be up, yep. But now follow along, take your hand. That force up is going to cause this V to change. And if the V changes, that means your thumb needs to change. And then how do you change your thumb without changing where your palm is, right? So again, a force up is going to cause it to accelerate up. So its velocity is going to change to be more up, right? Okay, but now follow along with your right hand. We're going to have that push. What does a force cause? Well, it causes an acceleration. So it's going to cause the velocity to change to be more upward. Now, as that velocity is changing to be more upward, right, what does that mean for our hand rule? That means your thumb is going to be shifting upward. Now, you can't shift your thumb and keep it perpendicular without also shifting your palm, right? So that means the force is also kind of changing. It's going more in. So the force is going to get more and more left, and then it's going to get more and more down and down and down, and then it's actually going to get right and right and right until, right, we've kind of ended up right back where we started, where we have a velocity that is to the right. So why is that happening? Again, because as you move your thumb, you will see your palm is also changing, right? So at each point, because the force is perpendicular to the velocity, you can see it kind of, it's a center seeking, it's a centripetal force. And so once we have this circular path, what are we looking for? We're looking for what is the radius of that circle, right? So r equals question mark. Okay. Let's go ahead and actually figure out what the radius is going to be. So what kind of motion do we have here? We have circular motion, right? So we have Fc, okay, equals, what is the centripetal force here? Well, the centripetal force is, as you can see, right, at every point, the center seeking force is the magnetic force. So Fc equals Fm, okay? And then we just have to think about the expressions we have for both of those things and solve for our notes. So Fc is going to be, always, this has not changed since Physics 20, mv squared over r, which again is just m times ac. So Fc equals mv squared over r is not on your formula sheet, but F equals ma is, and ac equals v squared over r is. So it kind of is on your formula sheet if you can put it together. Okay, equals Fm. This is a free charge, so it makes the most sense to use Q V perpendicular, which in this case is all of V, right? All of V is perpendicular to the field, so we're good there. We can just use that V perpendicular equals V. All right, so what are we looking for? We're looking for R, right? We're looking for R, so let's just multiply both sides by R, and then we can divide both sides by QVB. So we will have, in the end, okay, R equals mv squared over q the magnitude of B, okay? Do some cancellation because this V, right, is the V of the electron, right? It's the, yes, it's the tangential velocity, but that's just the same velocity it entered with. It's just being caused to move in a circle. Okay, so V squared over V, same V, see you later. That means R equals mv over qb. We already kind of derived this, but it doesn't hurt to do it again. Okay, so then just plug in. Okay, so the radius of curvature then is equal to the mass of an alpha particle. So on the back of your formula sheet, the mass of an alpha particle is 6.65 times 10 to the negative 27 kilograms. Okay, E is the 85% the speed of light, so 0.85 times 3 times 10 to the 8 meters per second. Okay, all divided by QB. What's the charge of an alpha particle? Well, it's 2e, or 2 times 1.6 times 10 to the negative 19 coulombs. And B, we were told, is 1.2 Tesla. Okay, quick unit analysis here. For the unit analysis, I'm just going to say, hey, remember what a Tesla is? It's a kilogram per coulomb second. I'm just going to kind of write that below so we can do our calculation, our cancellations here. So kilograms over kilograms, nice. Okay, those are gone. 1 over seconds, over 1 over seconds, those are gone. Then we have coulombs times 1 over coulombs, those are gone. What are we left with? Just meters, which means essentially Teslas are gone, right? If kilograms per coulomb second, Teslas are gone, leaving us with just meters. Hey, what are the units of a radius, of a distance? That is a meter. So R equals, if you punch that all in your calculator, I got 4.4 meters. Now we kind of already, without even doing any math, we kind of already determined this thing's path direction, right? What is its path direction? Well, clockwise or counterclockwise from our perspective, right? That would be the opposite way a clock goes. So 4.4 meters, counterclockwise motion. Here's one that brings in some of chapter 11, okay? So an electron is initially moving south at 1,000 kilometers per second when it passes two parallel plates with 2,000 volts difference between them. So 2,000 volts of potential difference between them. In other words, as it passes through that those plates, it's either going to gain or lose 2,000 joules per coulomb of potential energy. So the accelerated electron, it's going to either gain or lose 2,000 joules per coulomb of potential energy. And gaining or losing 2,000 joules of potential energy is the same as losing or gaining 2,000 joules of kinetic energy, right? Okay, so the accelerated electron enters a perpendicular magnetic field and moves clockwise with a diameter of 4.5 centimeters. Careful, that's tricky. That's a mean trick. Diameter of 4.5 centimeters. Useful, but don't forget R equals D over 2. So in this case, that would be 2.25 centimeters, right? D does not appear, diameter does not appear in our equations, radius does. So we're trying to figure out what is the magnitude and direction of the field. Okay, so we have to make an assumption here. It says accelerated electron, but remember, being slowed down or being sped up is accelerating. So let's go ahead and say that this field is going to make the electron go faster. Okay, so let's just try and visualize this here for a sec. We're going to have it's going to be able to pass through some plates. Truthfully, this setup kind of wouldn't work the way we're drawing it, but just to allow the electron to actually pass through. It has a VI here, so let's pretend this is south over here just to make it easier to draw. So VI equals 1,000 kilometers per second, which is 1,000 times 1,000, or 1,000,000 meters per second, right? Going this way. So if this thing's going to get accelerated, which way is the electric field? Well, remember, defined as what a positive charge would do. So there's our electric field. And also, it's going to speed up our electron, we said. So that makes sense. It should be against the electron's motion because, right, an electron will do the opposite of what the electric field kind of direction is because it's negative. Okay, so the electron's going to go through there. It's going to get sped up. Then whatever V it ends up with here, right, at the end is going to be the V that it enters some magnetic field with. Okay, so it enters some magnetic field. We can't draw the magnetic field yet because one of the whole points of the question is to figure out what the direction of the field is. So first, let's just draw the path and then we can kind of backwards think to what the field direction must be. So it enters a perpendicular magnetic field with some V, which is really the VF from here. Okay, so the VF after passing through. Okay, so V, we don't know it, but it's going to be the VF from there. We can even call it VF if we want. Okay, so VF, and then it enters this magnetic field and moves clockwise. So it now moves clockwise. Okay, so how does a clock move? Well, it goes to 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock, 6 o'clock, blah, 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 blah. Okay, that's kind of what its path is going to look like. And it does that with a diameter of 4.5 centimeters. Don't fall for that trick. That means we are interested in the radius, which is 2.25 centimeters. Okay, great. So take the appropriate hand out. Okay, is it going to be your left or your right? Now point that hand, the thumb of it, right, the way you should, and think about the force that this thing felt, and what do you get for your magnetic field lines? Well, when I'm doing it, I'm getting that my thumb, my left thumb is pointing to the right of the screen. My palm, initially, the direction of the force should be down to get this kind of path, right? And then as we go, it kind of gets pushed in along the way, just kind of squeezed in the whole way around, okay? So what do your fingers need to be like for that to be the case? I don't know about you, but I'm getting that my fingers would need to be into the page. Okay, so there we go. We already answered the direction just with our hand rule. They would need to, the magnetic field would be into the plane of the page. Okay, now to get the magnitude of the electron, we know that the magnetic force equals the charge times the perpendicular component of its velocity, which again is just going to be the whole velocity this time, times the magnetic field. And we know that since magnetic fields, if it's perpendicular, causes circular motion, we know that, well then, mv squared over r equals qvb. Okay, and so since we're looking for b, we'll divide both sides by qv. And again, that's the same v, so let's just go ahead and do that now. So then our magnetic field equals mv over qr. Okay, great. We got r. We know q for an electron. Okay, we know the mass of an electron. Those are on our periodic table. Problem, we don't know v, right? Because really that's this v. That's vf, right? That's vf. Okay, but if this was chapter 11, right, you've done this problem quite a few times. If it enters with this speed into some electric field with a known potential difference and you know the object's charge, can you figure out its change in kinetic energy and therefore its change in speed? Yes, you absolutely can. Okay, so our mission now is to find V, okay, so that we can plug it in there. So find VF, we can call it if we like, okay, which is really just the V that it enters with, which of course is V perpendicular. Okay, so how would we do that? Well, we know that the potential difference, the voltage, is equal to a change in potential energy divided by the charge of the object traveling through the potential difference. In other words, joules per coulomb, right? The definition of voltage. Okay, change in potential energy. Why? What is potential energy changing into? Well, in terms of magnitude, that is equal to the kinetic energy, right? Because all that potential energy is not disappearing, it's becoming kinetic energy. So mathematically, that is true. Change in kinetic energy is just EKF, what it ended up with, minus what it started with, EKI, divided by charge still, which of course, EKF is equal to MVF squared over 2 minus MVI squared over 2. That's just the numerator divided by the charge. So let's think about it. Do we have everything we need? What are we looking for? We're looking for VF. Got M, right? Know the mass of an electron. Got VI, they gave us that. Got the charge of an electron, and we have the voltage. So this is solvable. I'm just going to move it around a bit. Okay, so let's multiply both sides by Q. So we have, right, multiply both sides by Q. Okay, looks weird because there's a whole bunch of middle stuff, but don't let that bug you. So we have Q times the potential difference is equal to MVF squared over 2 minus MVI squared over 2. Okay, you could manipulate this in a totally different way. I'm just going to make my life a bit easier here and make it a few less steps. Let's just pull out, notice M and M, those are the same, right? It's both the mass of the electron, of course, over 2, that's the same. So this is essentially, right, it's the same as M over 2. If I pull that out as a common factor, VF squared minus VI squared. Okay, if you're not okay with that, just go ahead and add this to both sides and then do it the usual way. I'm just going to do that because it's going to save me a little bit of time. Honestly, not that much time. Okay, so Q delta V equals M over 2 times VF squared minus VI squared over 2. Don't forget, what am I trying to do here? I'm trying to get VF squared. So first, I need to get rid of everything outside the bracket. So let's just multiply this whole side by, okay, 2 over M. 2 over M. You see what I'm doing there? By multiplying by 2, I cancel that out. And then by multiplying by 1 over M, I cancel that out. Can't multiply that side by 2 over M without multiplying this side by 2 over M. There we go. Okay, let's just rewrite what I got. So 2Q times the potential difference over M, right? Just multiplying that over that, equals VF squared minus VI squared. Now, what's happening to VF squared? Why isn't it alone? My VI squared is being subtracted from it, so the opposite of that is adding VI squared. Add VI squared, okay? And then we got VF squared, just bringing this to the left side, equals 2 times the charge times the potential difference, all over the mass, plus VI squared. And don't forget, we didn't want VF squared, we wanted VF. So square root both sides, the whole thing. You're going to square root that whole thing. Do not make the mistake of saying, oh, VI squared and the whole thing's being square rooted, so I can cancel out that square. No, only if just VI squared is being square rooted. This whole term is being square rooted. Okay, you wouldn't do it in math, don't do it in physics. So VF equals the square root of 2Q times the potential difference over M plus VI squared. We know all that stuff. We can solve this. So VF equals the square root of 2 times the charge of an electron is 2 times the magnitude of the charge of an electron is E, right? The elementary charge. Okay, the potential difference was given as 2,000 volts or joules per coulomb divided by the mass of an electron on the back of your formula sheet is 9.11 times 10 to the negative 31 kilograms plus VI squared. VI was 10 to the 6 meters per second, right? Just 1,000 kilometers times 1,000 meters in every second for a million. Okay, don't forget that squared. The whole thing is square rooted. And if you put that all in very, 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 very carefully, you should get that. VF equals 26524,040 or 26,524,040 meters per second, which is a big number, but not faster than the speed of light, so we're okay, right? If you get something bigger than the speed of light, something went wrong, or whoever made the question was not very careful about the numbers, but you should never get something faster than the speed of light. Okay, anyway, here we go. We have VF. Why did we find VF? Let's remind ourselves. What was our plan of attack here? We found VF so that we could put it in here, right? Because we know the radius of curvature. We want to know the magnetic field strength. We know the mass, right? We know the charge. The only missing thing was the velocity at which it entered to produce such a radius of curvature so that we could figure out how strong the magnetic field must have been. Quick unit check, and this is the perfect time to do unit checks, is when you've done a lot of manipulation like this and you're hoping, oh boy, I hope I didn't make a mistake somewhere along the way. Well, don't just hope. If you got time, check. And if your units work out, you probably did okay, okay? So just going to do off to the side. We have coulombs times volts, okay? Coulombs times volts over kilograms, and then that's being added, which doesn't changed the units, but added to meters squared per second squared, okay? Because those meters and seconds are being squared, okay? So then we have coulomb volts. What's a volt again? In standard units, it's a joule per coulomb. So we have a coulomb times a joule per coulomb over a kilogram plus a meter squared per second squared, okay? So coulombs. Now we have a joule per kilogram, meter squared per second squared, okay? So kilogram, what's a joule? It's, well, the easiest way for me to remember it is that energy kinetic is mv squared. So it's a kilogram meter squared per second squared over a kilogram. Okay, this is looking good. The kilograms cancel, and look at what we're left with. Meters squared per second squared plus meters squared per second squared. That's not going to change anything, right? That doesn't change the units. If you have 2 meters and you add a meter, you have 3 meters. The units don't change. Don't forget this whole thing, right, which I really should have been doing from the beginning, was being square rooted. So we have the square root of meters squared per second squared. What's that? Meters per second. Our units check out. Okay, so when you do a whole bunch of manipulation like that, that's the perfect time to lean back on your units, have them check your work for you. Okay, so let's just say unit check. So going back to this, we already manipulated for this, so I won't do it again. Magnetic field strength is equal to mv over qr, vf, I guess, right? Even though it's the velocity it enters the magnetic field with, it's the vf of the plates, equals the mass of an electron, 9.11 times 10 to the negative 31 kilograms. VF we just found to be 26524,040 meters per second, all divided by 1.6 times 10 to the negative 19 coulombs, the charge of an electron, times the radius of curvature it had, which be careful, was not the diameter of 4.5 centimeters, it's half that, so 0.0225 meters. Okay, and when you do that, I got that. It is equal to 0.0067 Tesla. Okay, quick unit check. Meters over meters. Quick unit check, meters over meters. Cancel. Kilograms over seconds over coulomb. So kilograms over coulomb seconds. Hey, that is a Tesla. That's good. All right, you can now try the entire 12.2 assignment. There's nothing really in there that you haven't seen now. Just kind of my advice, most of this stuff, honestly, boils down to setting FC equal to FM. Yeah, sometimes there might be some weird stuff where you got to figure out the V, but most of this stuff is that the centripetal force is the magnetic force, right? And you have some equations for both. Okay. Okay, and then once you feel good with all that, you are ready to take this week's check-in. Make sure you guys are asking me questions on Flex if you need me, okay? Miss you guys.